Hello everyone, my name is Stefano Alberico and today I'm gonna present you and talk about a very important component in a hardware security module, which is the random number generator. Now usually every time you try to generate random number with let's say a piece of software on a computer, on a laptop or on a phone, you're actually using a pseudo random number generator. So the problem is, to simplify it, is that the quality of this random number are actually very difficult to achieve on a software based. So you don't really have a really true random source of entropy or pure, chaos to actually trigger and generate purely random numbers. So that's why in software usually you have this pseudo, while when having a hardware component, hardware generator, you can reach what is called true random number generator, a TRNG. And also using this kind of components, you have to ensure that for example, the entropy is the highest possible that you can reach. And by entropy, basically we mean how much information density you can pack on a certain string of bytes or bits, but we will see now soon. So we will try to generate some number and excuse me, and we will also try some available software, open source, that could be used to validate a certain set of random numbers or bits that we will generate. First of all, so you can see now I have a Raspberry Pi 3 now here on this side. It's a Raspberry Pi 3B Plus, which is connected through this SPI links, which is basically 4 wires, is connected to our HSM, which is at the moment up and running. The other 2 wires are just the power, so the plus and minus to connect the Raspberry Pi power supply to our board, our PCB board, which runs our HSM in this FPGA chip. So inside this unit we have our HSM. As you see, there is a LED blinking, which actually is red, although here it doesn't look like so red, but that's what we call the heartbeat. So just to see, it's a useful little LED to inform that the board actually is up and running. The LED is controlled directly from the FPGA, so there is actually a hardware program running, or a hardware circuits, which is powering the LED on and off, so we can make sure the FPGA is up and running. There is also another LED on the other side, which is, there are 2 actually, there's one green which we are going to use, which is actually just indicate the traffic on the SPI link. So in that way we can see when the Raspberry Pi is talking to the HSM, we can see if there is traffic data going on, which is also an indication of good operation. So this is, again, when we do testing, is also very good to have that indication. This is similar to the LED on the Raspberry Pi that shows when there is activity on the micro SD card. Okay, so the setup it's up and running, and now we are gonna see on our terminal window. So in here we have actually our HSM's command line interface, and this is at the moment running the version 1.3. As mentioned previously in other videos, we are of course keep improving and updating this API, so this version might change actually quite quickly by the time you will actually get the API and the hardware in your hands. So let's start with this. It's the first function, actually, the most straightforward in your face. So it's the -n, which is actually generate random numbers. So this function triggers the true random number generator module inside FPGA, which is actually composed by a set of oscillators, which are, let's say, in a sort of meta state, and this meta states and uncertainty actually is the source of the what's so-called source of the random number generator. And to call it, so we can just use the option n, and then we have to indicate how many bytes of data we want. And these are, so for example, if I mention 1 byte, it means 8 bits. So we are generating, because the random generator generates actually bits, casual bits, 0, 1, so it's a sequence of 0, 1, as long as we want. And we indicate this length by number of bytes. And the strings actually save automatically in a file, which is in the same directory where we are operating, which is called random bits, unless we indicate directly with the option O, we can directly indicate a file name. So we can actually generate another string, file name string containing those random numbers. So just very, very simply, and you can see now we don't have anything available except this other software Ent, which I'll come back to this a bit later. So if we now try very simply option N and we say just 1 byte and we run it, then we have a file, random bits, which contain 1 byte of random bits. So we have 8, 0 and 1. Now, to make this, of course, a bit more interesting, we can actually generate a larger number of bits, or random bits. So, for example, let's say we want to generate 1,000. So now, when I will press enter, this will be rather quick. We can actually even see how fast we can generate these bits. And probably now, I don't remember how fast this will be, probably less than a second. But you can keep an eye also on the green LED on top of the chip that will switch on, become green while this operation is executed, because of course when the module inside the FPGA is running, it generates the bits which are sent outside through the SPI link and directly saved on the file. So there is activity on the SPI link. Now let's go. Yeah, this has been actually very fast. And so you can see less than actually 1 cents of the second. So we have there our file of basically 8,000 bits. Let's make it now this, rather longer. Let's do 100,000 bits. So we can say how long it takes, and we can see the LED also going on. Now the LED is on and went off, so it was quite quick, but it's 0.2 seconds. And we can see, of course, the file has been generated 100,000 bytes, which basically means 800,000 bits. Now let's do, this is 100,000, we can go even to 1,000,000, or even let's say 10 million bits, or 10 million bytes, which is 80 million bits. So this is 10 million bytes. We can try. So now it's running. The LED, as you can see, is on. This is now running for some seconds. It's definitely longer than before. So again, we are generating a file which is saving in a raw format, basically the 8 million bits one after each other. So once we get this, then we can also analyze the quality of this string to see how actually is performing the random number generator. So it took about 27 seconds to generate 8 million bits. Now we can run this command end, who is actually performing a series of operation to, let's say, verify the quality. And there are actually 5-6 different operation running. Let's try. Now we just have to give one switch, which is the B, to indicate our file is actually just a string of bits. and then we give the file to run. So this is now running, and it's running now in software in the Raspberry Pi, so it's analyzing the file directly on our Raspberry Pi. And here are the results. So this is quite interesting. So we see already the entropy, and the entropy is indicates already that we have the maximum possible entropy. So the quality is the highest you can get, because you get 1 bit per bit, so you can't have more information than that. And this is already a good, factor, a good indication of the quality of the random generator. And if, for example, you would take this file, exactly this, and you would compress with a tar zip or something, whatever compressor, you will actually not reach any compression, because that's exactly one of the tool you can use. Because if you use a compressor software, file compressor, if there is any possibility to compress, it means that the bytes in size or the content is not completely random. That's why you can compress. So you find occurrence or maybe same character or same bytes, and then you can try to replace them with some code. So the fact that you can't compress them, it's an indication that the file is fully random. And the indication is exactly by this. So we have 1 bit per bit again of information that you can carry. And this is the highest you can get. And in fact, if you try to compress this file, which is this amount of bits, 80 million, then you would compress by 0%, which is the same as saying the entropy is 1. Now, the next is another calculation, which is, or a test, which is called this chi-square, C-I-H-I, chi-square. It's a very, very common test for, let's say, random data. Typically, this is used to check the pseudo-random generator, and it can actually identify very, very quickly when a string is actually generated by a pseudo-random number. So this test, it actually generates one number, in this case 0.24, it's an absolute number, and then it will give you a percentage, an indication of what is the probability that the next sequence or a sequence will be above that number or below. So in a way this is a little bit complex to understand, but the main point is that this percentage should not be very high or very low. So something like between, let's say, 0, 1 or 5 and 10%, let's say 0 to 10%, and the opposite between 90 and 100%, it's an indication that the number is pseudo. So now the next actually so in our case we have actually 62.59%, so it's far away from the extreme, so far away from 0, 10% and 900, and so that means it's the distribution has a good quality. And the next one is actually typical mean, typical mathematical mean value. So if I throw a coin, and let's say the coin is 0, 1, many times, on average, I should have a value which has a mean value of 0.5. That's the best you can get. In fact, in our case, so after analyze those 8 million bits, what we get is 0.5, which means the number is truly random. The next test, it's actually very interesting. It's called it's very famous. I mean, they're all quite known test. It's the Monte Carlo value. So in this case, what you do is this: you actually take a sequence out of your string. You take a sequence of 24 bits, and you use them to plot. Let's say the coordinates of basically a dot, to plot these coordinates within a square. And so basically those are random coordinates of a certain dot and a plot that you do within a square. And then you take the next one and the next one and so on. And when actually the dot fall within a circle which is contained inside the square, then you consider this a hit. So in a simple way, what you do is you keep getting those coordinates x and y, and then you keep plotting these dots in your drawing. So there is a square, and within you actually plot these coordinates. If you do that, you know, hundreds of times, thousands of times, hundreds, thousands of times, slowly you are approximating actually a draw of a circle, which is perfectly contained within the square. And so more, let's say, better qualities when you are approximating the pi number. So in our case, after 80 million bits, we can say that we are approximating the pi number with an error of 0.04%. So it's pretty small error, which means the accuracy is very high. This is actually asymptotically, you know, going to be more precise. So more number more random number you throw, and more precise will become this calculation. And the last one is called serial correlation coefficient, and basically it's this quantity measures on which extent each byte in a file, in this case each bit, depends from the previous one. So when this number is very low, or as low as possible, then means you have basically uncorrelation between the bits. So our case also is extremely low, and that means its quality of this randomness is very high. And then again, so this is actually the last of the test. So they all combine in one. And so this is again to those are basically tests performed of these 80 million bits, which are not actually an extreme high number. We could actually generate also much bigger. Now will take, of course, a large amount of time. We have tested with hundreds of millions. It takes, you know, we go around a few minutes. I might do another video where I show this, but I just wanted to do in real time. So this will end this presentation, and thank you very much for listening, and hope you enjoy this work. Thank you.